right, good morning, guys. So today we're going to take a look at lesson 10.3, talking more about circles and chords within circles. So the first theorem we have, oh, by the way, I will post my notes, the answer key to my notes on Google Classroom. It's actually a very quick lesson. We just have 4 quick theorems to go through, and then you'll work on some practice problems related to these theorems. The first theorem is called the congruent corresponding arcs theorem, which says, in the same circle or in congruent circles, so you could be looking at one circle or 2 separate circles, 2 minor arcs are congruent if and only if their corresponding chords are congruent. So keep in mind it's an if and only if biconditional, so the conditional and the converse are both true. All right, so basically, let me draw an example. If we have a circle, and if we have 2 chords that are congruent to each other, all right, so we'll call this chord, what do I call it? I want it to match my notes, AD, and this one is BC. Now keep in mind, not drawn to scale, but let's say that this chord is congruent to that. We can say that they're both 10 units long, all right? If those 2 chords are congruent, this theorem allows us to conclude that the minor arcs AD and the minor arc BC are also congruent to each other. And again, the converse of that is true as well. If you're told that the if you're told that the arcs are congruent, you'll be allowed to conclude that the chords are congruent. All right? So, in my notes I said, since AD, segment AD is congruent to segment BC, all right? They are both 10 units. All right, that allows us to conclude, therefore, chord AD, arc, keep saying the wrong thing, arc AD is congruent to arc BC. Okay, and again, the converse of that statement is true as well. Okay, so that's theorem number 1. Let's move on to theorem number 2 for today. All right. So this theorem, just give my board a second to dry, is the perpendicular chords bisector theorem. All right, and this theorem says, if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. Okay, so I'm going to set this up as like a given. So if I'm given a diagram that looks like this, okay, I have a circle, and then I have, I'll put my diameter first. And then I have a chord. Okay. And it says, if the diameter of the circle is perpendicular to a chord. So if I'm given a diagram that looks like this, then what I'm allowed to conclude is the following. So I'm going to redraw that diagram. I have my diameter, and it's perpendicular to a chord. So what I'm allowed to conclude is that the chord is being bisected, so those 2 segments are congruent, and its arc, its minor arc, is being bisected. Okay, so for instance, you might be told that this chord is like 20 units long, and then you could say, okay, well that means that that's 10 and that's 10. Maybe you'll be told that this is 160 degrees, and then you would take 160 to get 80 and 80, okay? So that's the kind of information you'll be allowed to conclude given this type of diagram. All right, theorem number 3 for today. Actually similar to what we just discussed. All right. So this theorem is the perpendicular chord bisector converse, which is why I said it was related, right? Because it's the converse of the one we just talked about. So this one says, if one chord of a circle is a perpendicular bisector of another chord, then the first chord is the diameter. So, for instance, if you're given something like this, okay, if this chord, it's a chord, okay, bisects and is perpendicular to this chord here. So if I'm given something that looks like this, all right, I'm allowed to conclude, since this first chord is perpendicular and bisects the second chord, that means the first chord is the diameter. It's going through the center, okay? And we'll give them names just so we can talk about them more easily. A, B, C, D is what I call them in my notes. So if AB is the perpendicular bisector of CD, that means that AB is the diameter. So then I could say then AB, segment AB, is the diameter of the circle. Okay. All right, and the last theorem for today. All right, so the last theorem says this. Oh, it's called, let me write it up, what it's called. It's called the equidistant chords theorem. Okay, so we're going to start with the circle. All right, and it says in the same circle or incongruent circles, two chords are congruent if and only if they're equidistant from the center. Okay, so let's have my center here, and let's have a chord here and a chord there. Okay, and let's say we measure from the center to that chord, that distance, and we'd always use a perpendicular straight line. Okay, let's say that this distance from the center to the chord is 5 units long, and this distance from the center to the chord is also 5 units long. Well, if that happens, if those two distances are congruent, this theorem then tells me that the chords are congruent, and I'll name them AB, CD. All right, so if this is what you're given, then what you're allowed to conclude is that AB is congruent to CD. Okay, and the converse, because it's a biconditional, it was an if and only if theorem, the biconditional statement is true as well. If you're given that this length CD is equal to this length AB, then you know that the distance from the center is congruent. So you would know that this little segment is congruent to that little segment. Okay? And that is our quick and easy lesson for today. So you're going to jump on over and do some textbook problems. And then we're going to have a few days of review of this lesson and the previous two with some worksheets. So I will see you guys later. Bye.